Okay, now we can start. All right, cool. Welcome back to the Santa Cruz Artificial Intelligence Club. This time for winter 2023. Happy New Year to all of you guys. Hope you guys all had a great winter break. Excited to see you all again. If you're returning, if you're new, welcome to the club. We've got an exciting quarter in store for you guys, and we cannot wait to share all of it with you. So today, we're going to be pretty much doing a quick little info session on what the winter is going to entail. And then following, we have our kind of first kind of topic on general neural networks, and we're going to dive into perceptrons. So let's get this thing rolling. All right, so first, want to make an announcement. It's an exciting time for the club. It's the new year, so we thought let's start off with a brand new logo. We're a new leadership group, new everything. So we decided it's time for a rebrand. So our logo challenge winner Neil, he designed this logo for us, and we think it perfectly encapsulates what we're all about and what we want to do forward. So this is our new logo. You're gonna have to click it. There we go. Awesome. Thank you, Neil, for designing that logo for us. We're gonna be changing this on our website, Instagram, everywhere, following the meeting, and starting to really kind of use this everywhere. So we're super excited to have this new logo for us and for the club moving forward. And we want to thank Neil for designing it for us. So let's get into some more logistics. Today's a Tuesday, and if you were here last quarter, you're kind of confused. We were meeting on Mondays. This quarter is a little bit different. We had to change some of the timings around just for our sake and for many of people who couldn't make it last quarter as well. So we're changing the time, not the time, we're changing the day to Tuesdays from 6 to 7. Normally, we will be in Baskin E2 180. That's where we usually meet. It's just because of the storm and because of the current conditions, today we're on Zoom. But going forward, we will be in E2 180. We will be in person, and excited to see you all in person finally for the new year. All right, so what are we going to be doing this quarter? So if you remember last quarter, we were doing the clustering system where we took 2 weeks to go 1 week. We're going to do a topic. We're going to introduce a topic to you guys. And the next week was our kind of lab week where you guys we'd give you guys a collaboration notebook and you guys would do the project on your own. So this time we're going to do it a little bit different. We've got a jam-packed quarter. We've got a ton of new topics, and we're going to be introducing a new topic each week and a new project each week for you guys to do. So week 1, so that's this week, we're going to be doing general neural networks and perceptrons. Week 2 is just more neural networks. Week 3, deep neural networks. Week 4, CNNs or convolutional neural networks. Week 5, recurrent neural networks or RNNs. Week 6, on long short-term memory on LSTMs. Week 7, when we talk about transfer learning and more. Week 8 on SVMs or support vector machines. And to round out our last 2 weeks, week 9, we're going to be talking about AI and ethics. And the last week will be our kind of finale for our competition, Sky is no limit. All right, so last quarter we had 3 speaker events, and just like with our topics, we want to do more. So we are increasing our lineup from 3 to now 5. So there's more opportunities for you guys to see how AI is being used in the real world, some real world applications, demos, to hear from people in the field right now, be able to ask all these guys some really interesting questions, hopefully, and learn something from them. So save the date for all of these dates here. So January 19th, we have Mr. Jayesh Lakoom, who is a product manager at Oracle. January 26th, we have Pranav Vempati, who was the previous president of the AI Club, who is a data scientist currently at the Lawrence Livermore National Labs. On February 2nd, many of you guys know him, Professor Luca de Alfaro, who's a computer science professor here. And then on the 16th of February, we have another professor here at USCSC, coming in to talk to you guys and to all of us, Professor Marinescu. And lastly, on February 23rd, we have Mr. Samal Sheikh, who was the COO of Drishya AI Labs in India. So exciting stuff. Hopefully you guys will be able to learn a lot from these guys. I know I certainly will. So please come to these and get a lot of information out of it and try and network, try and get a real understanding of how and where AI is being used currently in the field. Jonathan, you want to take it?
Yeah, sounds good. Okay, so as with last quarter, I announced the topic, manage the competition. I'll be doing that again this quarter. So for those of you who are new or don't remember from last quarter, Sky's the Limit is basically a development competition that we run that I came up with last quarter. Where the goal is basically based off of a vague topic and a loose interpretation of that topic to come up with some sort of machine learning implementation using whatever model and whatever data set that you can find. More than anything, this is an exercise in data science and data cleaning. So keep that in mind. It doesn't need to be something absolutely insane or anything incredibly revolutionary for your approach, so long as it is an interesting result and it is applicable to the theme that we cover here. It is more than likely going to fit with a little bit of review and tweaking from our end. But yeah, without further ado, the topic for this quarter is going to be, if it's here, there we go, brain teaser. So keep that in mind. We decided to go with brain teaser because we're doing a whole bunch of stuff neural network themed. We'll get into a little bit why that was specifically chosen, but the topic for this quarter is brain teaser, or the theme, I guess. So follow this. I'll be posting a few more materials as probably later this week with a bit more information for those of you who are interested. We'll also be posting a Google form for those of you who are interested, so we can have a bit more direct communication over email. But yeah, it's going to be a very good quarter, and I think the competition this time is going to be even better than the last one. All right, so without further ado, let's get into the material for this quarter. First, I decided that the best thing for us to do would be just to cover some general background information on neural networks. Basically everything that we're going to be doing is going to be neural networks this quarter, so I thought the best thing to do would be to cover some information about them generally. Aside from our weeks on support vector machines, ethics, and the Sky's the Limit competition, everything that we're going to be doing, so 7 of the 10 weeks are going to be based on neural models. So it's really, really important that we understand these basics, at least generally, before we go into a more deep dive in the following weeks. All right, so put simply, artificial neural networks, which is what we're going to be implementing this quarter, are an effort of biomimicry. Biomimicry in the sense that the original neural network was inspired by the human brain. On the left, you have basically just a very simple biological neural network with a cell body, dendrites that take a lot of the inputs in, and axons that fire electrical impulses to the ends of the nerve cell to emit some chemical transmitters. In this way, it's very, very similar to an artificial neural network, and we'll get into exactly why in a moment. But this effectively inspired the field of neural networks and every advancement that comes with this. You'll see later when we cover CNNs that there was another element of biomimicry there, and I believe also with RNNs. I might be wrong about that, but point is, biomimicry is everywhere in this field, and this is just one very simple example for how it was inspired. So as a direct one-to-one comparison as well, the cell body of a nerve cell can be pretty much directly compared to an activation function, which we'll talk about in the next slide. The axon, which carries the electrical signal to determine what chemical transmitters are sent, is the output of the function, and dendrites are the inputs into each neuron in the network. Very, very simple. It's a bit of a dumbing down of how the biological process actually works, but this is basically how an artificial neural network works. So the activation function, more or less, the activation function is a way for us to figure out what sort of output, if any, should come from the inputs that we're giving into a neuron. So if we take however many inputs that we have, multiply them by some weight, we can figure out whether or not our neuron should give us any sort of output using one of these activation functions. Now there's 6 on the screen. These are generally used a lot, but realistically, any function that is differentiable can be used as an activation function, or that is just real defined. So if you can think it, you could probably use x squared or x cubed minus 3x plus 1. All of those are valid activation functions. It's just getting it to fit your system. And these are commonly used because they're very, very effective. Sigmoid we'll get into later. Cohen next week will be covering sigmoid, 10H, and ReLU in a lot more specificity. But for the exercise we're going to be doing today, we're going to be using sigmoid, but you can experiment with any activation function. So this more or less is how you actually calculate whether or not there is an output using that information. So at the bottom there's basically the equation that's used for every neuron of a neural network. So the omega is representing the vector of weights, the x is the vector of inputs, the dot between them is the dot product plus a bias. So that can be interpreted, if you go slightly further to the right, as the sum. Here, actually, let me use a laser pointer. This might help. So the sum of each term in the weight vector plus each respective term in the input vector, or sorry, times, summed together, plus an individual bias term for each neuron, which is represented here, gives you this sigma, which is your sum. And that is basically what goes into your activation function to determine if there's an output. So if you take, for example, the sigmoid function, if you plug in a value of 4, you're going to get a value very, very close to 1. And if you plug in a value of -4, you're going to get a value really, really close to 0. For 10H, it's going to be really close to 1, and for -4, it's going to be really close to -1. So all these are their different use cases, but more or less, this is how every neuron calculates what should come in or out of it. So what goes into the activation function and what comes out. It's fundamentally that simple, and we'll see today where that originated from. And this gets us to the topic of gradient descent. We mentioned this very briefly last quarter when we were starting just to cover everything generally. Gradient descent is very, very important for neural models because neural models, you don't know what the equation you're trying to fit is, and it can be very, very complex. By nature, neural models can have hundreds of thousands, if not hundreds of millions of parameters that can be tuned. So you need to fit a model over time. Gradient descent is really efficient at doing that. More or less what you do is you define an equation to evaluate the fit of a model. So this, a lot of the time, is just taking a prediction from what the model thinks should be the output, comparing it to what you know the output is, and then doing some sort of score to see how accurate it is. And by doing gradient descent, you basically just follow the curve down to where the error is minimized. We'll get into more detail as we go along because this is used everywhere, and there's a lot of different methods to do this. But gradient descent at its simplest is just define a function to determine the fit of your model and then follow it down to its minimum. And that is fundamentally what drives all of modern neural networks and computing that use sort of learned behavior. Okay, so all that's basically just introduction. And this takes us to our first project, actually. So we're going to be doing a very simple cat versus dog classification. The data set that we're going to be using is, I think, 55 images of dogs and 55 images of cats. Each one, I think, is around 20 pixels by 20 pixels each. They're both in black and white. I don't remember if I mentioned that. So feel free, if you know or if you don't, what a really efficient approach to this might be. Take a couple minutes, think about what you might want to do. Rahul, if you don't mind setting up a couple breakout rooms that people can put themselves into as well, that would, I think, be really good for spurring a little bit of discussion. But yeah, don't feel pressed.
Absolutely.
Yeah, don't feel pressed if you don't have a really great idea of what might be an excellent solution to this. We're going to get into a lot more advanced ideas as we go along. But for now, just take this in stride and take an opportunity to think about how you might approach this. Oh, sorry.
Should all got in the breakout rooms?
Okay, doke. So close that in about 2 minutes or so, and I think we're gonna keep going.
All right, for sure.
Also pause the recording real quick, just so there's less dead air.
Should be on.
Yep. All right. Are all the breakout rooms closed at this point?
Yeah, they should be.
All right, sounds good. So does anyone have any ideas of some potential approaches to doing this sort of classification? Feel free to unmute yourselves as well.
I mean, the way I see it, at least with the current neural model that we've been told about, you would just treat well, the images was, I think it was like 20 by 20 and black and white, right?
Mhm. Yep.
So via that constraint, I think we can choose to be not super intelligent with it. I guess we could just have the inputs be like 400, which 400 inputs, which are just a 0 black, 1 white, and then grays in between on the left side, and then some nodes in the middle as the hidden layer. And the output would just be 2 nodes, one of them being dog or not, and one of them being cat or not, and you pick the higher confidence value.
Yeah, that absolutely would work. Just a vanilla neural network would totally work in this case. Actually, it might not, but just for reasons that we'll get into like later, like week 4 later. But that is a very good approach. Very, very good approach. Any other ideas? All right, we will leave it there then. So that is definitely a very possible approach, and it's similar to what we're going to be implementing today. What we're going to be doing is called the perceptron algorithm. This is literally the first neural network ever invented. It was invented in 1957, as the slide says there. The picture on the right is the original perceptron machine, which was constructed in 1958 or 9, if I remember correctly. More or less, it's 400 photoreceptors. So think just 400 small cameras that just detect light or no light. And those were randomly connected to mechanical potentiometers. So what it did is it did electrical gradient descent, which is completely bizarre for me to think about, like looking back. This was more than 60 years ago. And this is the basis for modern neural networks. For those of you who know a bit more about neural networks, that's why neural networks are often called multi-layer perceptrons, because you just add a whole bunch of them in parallel and then you stack them in series, and that's it. And so literally just by the miniaturization of computers and making things go a lot faster than they were 60 years ago, we're able to do this. So the only thing that's wrong with this algorithm is that it was way too early. Anyway, I digress. This is used only for binary classification. The perceptron algorithm, just based on how it's defined, it is really only useful for classifying a 0 or a 1, which is why it's pretty useful for the task that we're going to be doing today, because we're just distinguishing between a cat and a dog. At the top there is basically its activation function. We'll show it graphically on the next slide. But more or less, if the weights dot the input vector, so just every element in the weight times every element in the input vector and multiply together, summed all those up, plus some bias term. If it's greater than 0, then your output is 1. If it's not, then it's 0. And that's fundamentally it. This is still used today primarily in natural language processing. It's been picking up steam since I think around 2016. But it's still pretty cool in my opinion how something from more than 60 years ago has really been still used and is still being expanded on even today. It's fundamentally incredible. Anyway, so the perceptron activation function is very, very simple. It's called the sinum or unit step function. Basically, if the value going in is greater than 0, it's 1. If it's 0, if it's less than 0, it's 0. And that's it. It's very, very simple. The way to optimize this is just basically using the sigmoid function in place of it, which we'll be doing in our exercise later. But it is fundamentally very, very simple. There isn't anything complicated about how the perceptron works. You could code it by hand. The only difficult thing is implementing gradient descent. So you won't be doing that today. So extending this into multi-class classification. So in other words, how you would do this with more than one class. So instead of just doing cats and dogs, what if you wanted to also check if something is a fish, right? Oops, my bad. You would basically just do what's called one verse rest classification. So if you wanted to detect if something is a cat or a dog or a fish, you would just add more perceptrons. So the number of perceptrons equal to the number of classes. So every perceptron would then tell you if something is a cat or if it's a dog or a fish, if something's a dog, for cat or fish, etc., as the slides say there. And then all you would do is instead of using the sinum activation or the unit step function, you would use the sigmoid function, which is basically just probabilistic. So the nice benefit of this is because instead of using a binary classifier like the sinum function, you can use sigmoid, which is probabilistic. So so it tells you the strength or confidence of its classification. So if we're looking at the example we have on screen, if you have a picture that's shown, the first one could give you the probability of cat versus dog or fish of being 0.9 for cat and 0.1 for dog or fish. And then for the second one, dog could be 0.7 and cat or fish could be 0.3, and fish could be 0.6 and cat or dog could be 0.4. So then by comparing those values, you would think that it's a cat. But if you were just to be doing this with the normal sinum activation, everything would be 1. So the model would say that it is a cat, a dog, and a fish, which doesn't make any sense. So by doing a probabilistic classification in this way, we're able to get a lot more precision in our decision and get something that's generally better. So the bottom left is basically just an example of one versus rest classification. You just draw a whole bunch of boundaries, and that tells you what the classes are compared to all the other ones. And the bottom right is how you would apply that using the perceptron algorithm. So you use let me do this again. You use the sigmoid function for each of these instead of the sinum function. So each one gets its input times its own weight vector plus a bias term, which isn't shown here, to give you an output value here. And then those are directly compared with what's called an argmax, but argmax is just basically pick the highest value and that's your output, and that's it. Fundamentally very, very simple to scale up, and this is effectively the basis for a deeper neural network. All you do is you add more of them, like you just make the network wider, and then you can make it deeper by just adding more layers. And the nice thing about how the perceptron works is that you can infinitely scale it. You can just keep connecting things forward because the output of one cell can be the input for another one. And it's just impressive how you can just keep building it, and it's intelligently designed in that way. So all that being said, this is the exercise for today. There's a QR code in case you want to scan it on your phone. There's a link in case you just want to click through, but you can't. So scan the QR code, type the link into Google. It's https://tinyurl.com/sky-perceptron. And remember to make a copy of this. You should be able to access it if you're signed in with your UCSC account. Make a copy. There's about 7 lines of code that you're going to need to write for this. It's using Keras. So if you don't know Keras, everything they're going to need is linked in there, and it's spelled out pretty clearly what you're going to need to modify and where you're going to need to modify it. Going forward, we might be using Keras. We might be using other machine learning frameworks, but all of these are just good to pick up a little bit here and there. So this week, Keras. I think next week, Cohen, correct me if I'm wrong, you're using TensorFlow. So it doesn't really make a difference, but everything you're going to need is linked in there. It shouldn't take you more than 20 minutes max, and we'll be around to answer questions if you need. Actually, yeah, before you guys hop into this, are there any questions about the algorithm you need answered? Because I'd be happy to answer them. there in chat. All right. All right. And yeah, don't worry if you guys don't completely get this. This is a lot of new information to unpack. The main thing that you should be trying to pick up from this is how to navigate these resources. But aside from that, that is more or less it's. Rahul, you can actually stop the recording, and we're gonna, I think, break you guys up into breakout rooms right now, and
Yeah.
we'll be assigned to a couple here and there in case you guys have questions. But
Yep.
yeah, that is basically
We
all the
hopping around.
information today.
Create 4-3. Create.
Thank you, Colin, for sending that link. And the link is in chat in case you guys need to see it.
Okay. If you have any questions for me, let me know. I'm happy to answer.
Hey, so if I'm a complete beginner, what do you think I should be focusing on here?
Yeah, that's a lot of what. So how much of a beginner are you?
Like,
So do you have
brand new
brand new
com-
to AI, or do you have any
to
coding
AI?
experience or anything?
I have a lot of coding experience, but just brand new to AI.
Yeah, for sure. Yeah, so for someone in your position, I think for right now, you just want to kind of attend these, get a sense of it's not only just the actual algorithmic part, it's a lot of math as well. So just kind of understanding how does some of the math work, and how can I implement that uh, into into whatever project I'm doing. There are a
Okay.
lot of like really cool resources online, especially on YouTube, with some of these
Mhm.
AI courses that I can link you to. I can send you some links for those as well. It's what I've used
Sure.
before. The Stanford course
Mhm.
taught by Andrew online uh, is really, really helpful. At least it was for me when starting out. Uh, I'd also say that yeah, and it's just like practice, and the more you familiarize yourself with some of the tools, the more you'll get comfortable with it.
Okay, for sure. Yeah, if you could link those to me, I would be more than happy to take a look at them.
Absolutely. And everyone else here, would you guys also want those links as well? Give me a thumbs up, thumbs down. Yeah, all right. Sweet.
All right.
I'll send those to you guys. Also, forgot to mention, some our last quarter material is also still up. So if you'd like to take a look at those as well, we covered logistic regression, linear regression, clustering, and naive Bayes classifiers. So that is a lot more elementary than what we're doing right now.
Okay.
If you guys want to take a look at those as well, it's in our Discord. We have our slides, recordings, and collab notebooks up. for you guys to check out as well. So if you want to see those and kind of get a bit of a hang of it. And so I just put in the chat the Andrew Ng course, the Stanford course. This is what I used. I found it super helpful. The math can get a little scary, but trust me, it's not that scary. Hopefully, just a lot of worded symbols come into math. I thought it was just numbers. That definitely happens in the beginning. At least it happened for me. But he's really good at lecturing and really good at explaining the concepts. He'll start off pretty elementary, and then he'll really dive into it, and you'll get a full, well-rounded like understanding of that topic. And then there's one. There is this. I'm pretty sure you have to pay for the course, but it is also taught by Andrew Ng. But this is something else that has been highly recommended to do starting out if you would like to, and get more of a personalized experience, a lot more personal projects. Uh, then I would definitely check this out as well. Yeah, no problem. Right. Hey everyone. Hopefully you can hear me. Hopefully no one else is talking right now. That'd be weird. I'm gonna post a feedback form into the chat. Or actually no, Cohen, can you go ahead and do that? You have the permissions on it. So uh Cohen is gonna put a feedback form into the chat. If you guys could fill it out for us, it really helpful for us and making your experience that much better. It's an hour of your time. We want to make your time the best possible experience possible. It's said possible twice, whatever. Um, but if you guys could please fill out the feedback form, it'll really help us. And it's not working. Wait. Hey everyone, just hopefully no one else is talking, hopefully in the other breakout rooms right now. Uh, we're going to be posting a feedback form into the chat. Cohen, can you actually do that? I think you have permissions on it. You can just go ahead and put that in the chat. Please take some time, maybe like 2 minutes to fill it out. Your feedback is greatly appreciated. It helps us improve and makes your experience with us that much better. We want it to be the best possible learning experience for you guys, and your feedback is greatly appreciated. So if you guys could take maybe 2 to 3 minutes after this to fill it out and give us some feedback on how today went, that would be awesome. So yeah, Cohen, can you put it in the chat, and then you guys fill it out at your own leisure.